Welcome to tutorial number 5 over machine learning. In today's video, we're going to be going over testing and validation, how to deal with training sets and test sets as well, how to talk about generalization errors, and various other concepts. Now, this is going to be our last tutorial over conceptual ideas, really. Starting in the next tutorial, we're going to be going over how to create an actual end-to-end machine learning project. And we're going to spend several tutorials over that. And so we're going to actually begin opening the code editor, VS Code, or whatever IDE you use, and we're going to actually start building real world applications. But this is going to be our last lesson that's going to be primarily a conceptual lesson. But these conceptual lessons have been very important. We've gone over some general high level ideas. We've gone over different types of learning systems. We've gone over supervised, semi supervised, reinforcement. We've gone over batch learning. We've gone over online learning, different types of learning systems that we can use in order to train an AI model. We've gone over the problems that we face when training an AI model, such as insufficient training data, poor quality training data, overfitting, underfitting, all of those different aspects. We went over as well instance-based versus model-based learning. And here in our last video, that's primarily a conceptual video, a high-level conceptual video, we're going to be going over how the hyperparameter works and generalization errors and test cases. And so this is going to be our last tutorial going over this. And so we're going to begin that in our next tutorial. Moving on forward, we're going to actually begin coding. So let's go ahead and start off with our last lesson over testing and validation now. So let's talk about training an AI model. We talked about how we have a training set that we have in order to train an ML model. And we talked about different problems that we can arise when we have our training set. But when it comes to having our training set, we have to understand that our model may perform well in our training set, but may not perform well when presented with new instances or new cases that a user may ask. In order to prevent this from occurring, we can use a process where we separate our training set into a training set and a test set. And so we separate it into two categories. The test set will be labeled data. So it'll be supervised data that's already been labeled with a particular answer. The training set may be unlabeled or labeled or a combination of that. And so we're going to separate our data into labeled data with answers to those questions using a test set, and then maybe unlabeled data with the training set. Now, the training set might be partially labeled. We talked about semi-supervised learning with that. But the main idea is that we're going to separate this in order to not face problems when we're actually presenting it to a user. So when it comes to our test set, obviously the test set will be a collection of labeled instances. Now, when we test our ML model on these new test instances, we will get a generalization error. So the generalization error simply refers to the error between what the ML model is producing versus what we want the ML model to produce. Now, with each test set, since it's a labeled data, we would know what we want our ML model to produce. But if it doesn't produce that, then that error is called a generalization error. Now, we call it an out of sample error because the sample error is the training set. And so any error that the ML model makes when using a training set data, that's called in sample error. Whereas since we're using test sets, this is going to be out of sample, out of the training set. So we call that out of sample error. And the generalization error helps us determine the error rate for the model on instances it has never seen before. And that's the primary reason why we have that generalization error. Now, let's talk about the training error and the generalization error and what can we infer from that. If the training error is low and the generalization error is high, that means that the training model is overgeneralizing. Why are we saying that? Well, because if the generalization error is high, that means that the model is not performing well when presented with new instances. But if the training error is low, that means the model performs well on the instances that it is being given when it is being trained. And so that means the model is not able to generalize to new instances in our test sets, in our test set. And so that's very important there as well. It's overgeneralization, also known as overfitting. Let's talk a little bit about regularization and the hyperparameter then. So regularization basically refers to the fact that we want to reduce the number of parameters or the degrees of freedom that we allow our ML model to use. And so when it comes to these degrees of freedom, you have to understand the difference between a parameter and a hyperparameter. So a hyperparameter are parameters that the ML model is able to create as it's going through the training data, as it's trying out new instances of the training data. That's what the parameters are. It's what the model is learning as it goes through different training sets, as it goes to different training instances. The hyperparameter, however, are how the model will approach each of those individual instances, each of those individual training instances. And so you see an example here in the notes here, where we said that a hyperparameter would be the ingredient amounts adjusted while cooking. And so if you're cooking, let's say, you might change the ingredients based on the output, right? And that's what the parameter is. Whereas the hyperparameter might be things that you would choose before you cook, such as the temperature or the cooking time. And so that's what a hyperparameter is. The hyperparameter is set before you're training the model, whereas the parameters are what the model learns, is what the model is able to get when it learns the data, when it learns the new training instances. Okay, so that's the difference between a parameter and a hyperparameter. And remember, we want to use regularization in order to limit the number of parameters that we have, so that way we can generalize the information better. And again, we talked about generalization in our last tutorial. In our last tutorial, we talked a little bit about generalization when we were talking about the problems in machine learning. And so again, this will help us from overfitting the data. The hyperparameter will help us not overfit the data. So when we're talking about these hyperparameters, remember the hyperparameters are set before we train the data. When we are using these hyperparameters, we might be able to say, okay, we're going to train the data here, we're going to train the data here using this particular hyperparameter. Let's say we are able to get a hyperparameter that performs well on our test set, but it doesn't perform well on new test sets that the user gives us. So that may come as a result of the use of the hyperparameter being adjusted just to serve that specific test set. And so let's say our test set has certain characteristics or trends that are unique to it that is not necessarily true among the general array of test cases that a user can give. And so there's a trend in that test set that might not be true for all the new test sets. The ML model might observe some correlation where a correlation simply does not exist. And because of that, it may set a hyperparameter, right? We may design a hyperparameter. We might choose a hyperparameter that's a better one to choose based on that small test set without considering all different types of test instances. And so because of that, we use a process called holdout validation, where we simply hold out part of the training set and we test it on the rest of the training set, right? We test it on the rest of the training set. So the training set minus this part of the training set that we're holding out. And then after that, we will test the model on the one, we will test which model works best on the held out training set. So basically what we're going to do is we're going to take out a portion of the training set and we're going to test the model on a portion of the training set. And then we'll do that through several models. We'll try that in several models. And then we'll choose which model we think. We'll try all those models on this small held out part of the training set. And that small held out part of the training set, whichever one performs better, that is the one that we will choose as our hyperparameter. That model, depending on what hyperparameter we chose for that particular model. Okay, so that's what this refers to. And the held out training set is called the validation set. Okay, so now there is a problem when we have a too big or too small of a validation set. If we have too big of a validation set, that might mean that our training set is too small. Because remember, the validation set is simply the training set. The a portion of the training set, which means the training set minus the reduced training set. And so if our validation set is too big, that might mean that our reduced training set might be too small, right? And so because of that, there might be a problem with that when it comes to the amount of information we have to train the ML model. Whereas if the validation set is too small, that might result in us in us choosing a hyperparameter that might not work for all instances. And so we want to choose just the right size. But there is a solution to that, potentially not choosing a too big or too small validation set, and that is to use the process of cross-validation. So cross-validation is we take our training set and we divide it up into smaller validation sets. And so we'll divide it up into, let's say, 5 validation sets, and we'll have a reduced training set as well, right? So we'll have a reduced training set, and then let's say 5 validation sets. And so with our 5 validation sets, what we'll do is we'll train the data on the training set, and then we'll try it on each of the validation sets. And so what that will allow us is that will not allow us to observe a trend in the data that might not exist for all instances of that data. That's called cross validation, where we have many validation sets. And so the main idea I hope that you're getting from this is basically that what we want to do is we want to make a we want to create a training set that is resemblant of real world instances. That's our main goal, right? Whatever a user might input in a real world scenario, we want to try to account for as many different variations of what a user can enter in. And so that's the basic idea. And I'm going to go through this a little bit one more time, just that way we can explain this a little bit better, because it is important. It is an important idea. So again, we're going to go through this very briefly. Again, just reviewing this information a little bit more briefly. But remember, again, we have the training set, and what our training set is we're basically using that to train the model with different training instances. Now they might be labeled or unlabeled or semi-labeled or anything like that. Most data is semi-labeled. And what we're going to go ahead and do is in order to make sure that our ML model will work with new instances of data, is we will basically separate the training set into a training set and a test set. The test set will be labeled instances of the data. And once we're finished with the training set, what we're going to go ahead and do is we're going to test the ML model on new test cases that are labeled. And based on the discrepancy between what the test set wants us to get versus what the ML model is predicting, that discrepancy is called the generalization error. We call that an out of sample error because it is out of the training set. The training set is the sample. And so if there's an error in the training set, we call that an in sample error. Generalization error is out of sample. That's why we call it an out of sample error. And so the generalization error helps us determine the error rate for the model on instances it has not seen before. And remember, the key idea with the test set is that it is labeled instances of that data. If the training error is too low and the generalization error is too high, first of all, let's try to understand what that means. Generalization error being too high. What does that mean? Well, it means that the model does not perform well on new instances of the data. If a model does not perform well on new instances of the data, what does that mean? It means that the model is not good at generalizing the data. If the training error is low, that means the model performs well in the training set. That means that the model is observing a trend within the training set, but it is not able to do well on new instances of that data. And we saw an example with that. If you can go back to our previous lessons, where I showed you a graph where the model performed well on certain instances, but it wasn't able to perform well on all the instances. That's called overgeneralization error or overfitting. And so that's the main idea there. And we talked about regularization, basically, is where we're reducing the number of parameters. I believe that's called feature extraction as well. And this prevents overfitting of the data, right? And so we're reducing the number of parameters. A hyperparameter, remember, is set before the machine learning model is trained, and it controls, sorry about that, and the parameter is learned while it is training. So basically, the parameter is what the ML model is discovering as it is going through the training instances, whereas the hyperparameter is what we set before we initiate the training process, right? And so you can think about this: the parameter are the ingredients adjusted while cooking. The hyperparameter are the recipe settings you choose beforehand. And so let's just dive into that a little bit further, just so that way we can understand this a little bit further. Let's say you're trying to know what ingredients are best in order to make a certain type of food. Well, what we can do is we need to have certain hyperparameters, things that we choose beforehand. We need to choose, for example, certain constant factors, such as, for example, what's the oven temperature? How long are we going to be cooking? Right? There are certain variables that we have to keep the same throughout the entire process. And we choose those parameters beforehand. That's called the hyperparameter. So the hyperparameter is what we choose beforehand. But what we can do is we can cook certain food with certain ingredients, and then we can take that out and see how did it do on that particular ingredients that we put in. And then we see, okay, we can increase this ingredient or we can decrease this ingredient. That's called reinforcement learning, right? And we talked about that in our tutorial number 1. And that is what our parameters are, those ingredients that we adjust while we are doing that cooking. And then, so that's what it is. Hyperparameters are set before the data analyzed. So it really isn't that complicated when you think about it in that simple way, right? And so what we talked about as well, again, just reviewing this again, occasionally a model may perform well under a certain hyperparameter, but may not perform well on a new test set. This occurs because the hyperparameter was best for a specific test set. The model was trained with. And so what we talked about there was that a model may perform well under a particular test set by observing some underlying correlation in that test set that simply does not exist with the new instances that the user may submit. And so the solution to that was called holdout validation, where basically we held out part of the training set and we trained several models on a reduced training set. And so what we did there is we got rid of a certain portion of the training set, and then we trained the model on a reduced training set. And then once we were done, we trained the model on this new held out set that the model hasn't seen before. And that's called a validation set. And we call it a validation set because we're using that set of data in order to validate whether or not a reduced training set successfully was able to train an ML model in a proper way. Now, the problem with this, obviously, with the validation set is that our validation set, if it's too big, remember, if our validation set is too big, what does that mean? Well, the validation set is simply a portion of the training set. We train the data on the reduced training set. If the validation set is too big, then that means that our training set was too small. And that's obviously a problem. Now, that being said, on the converse, if our validation set is too big, that means our training set is too small. If our training set is too small, what does that mean? Sorry, I think I said that backwards. If our validation set is too small, that means our training set might be too big. Now, if our training set is big, that's okay. If our validation set is too small, you might see an error that there might be some trends within a small amount of data compared to a large amount of data, right? So, like, for example, let's say we were to look at cat images, okay, let's say, for instance, and we had to classify different cat images according to which, let's say, breed or something the cat was a part